Hi, I'm Professor Seth Chandler, and this is a discussion of operator pipelines and the query language within Wolfram Language. It's part of the course, Analytic Methods for Lawyers, but it's actually, I think, useful for anyone who's doing programming in the Wolfram Language or wants to learn how to handle data in the Wolfram Language. And the idea is basically most modern languages have something like the facilities discussed here. If you look at Python, there's pandas. There's SQL, which is basically dedicated to doing exactly what we're going to be doing today. If you look at R, it has dplyr and a whole tidyverse framework. Julia has data frames. And so the functionality that you see here is obviously required in order to do modern data analysis. And I'm going to show you how to use the key function in that framework, which is called query. Before we get to query, though, I think you need to understand the concept of an operator pipeline. It's a little bit of a different way of programming. As I say in the essay, if you want a one-sentence description of what query does, it's query produces a pipeline of Wolfram language operators in a way that makes complex data processing operations more concise. Let's start with the concept of operators and pipelines. So suppose we have a function and the purpose of the function is to multiply a number by 3 and then add 2. Well, I think this is how many of you and I would write it. You just say some function f1 of something or other which we'll name x, and then on the right-hand side of the set delayed operator there, we'd say, well, it's equal to 3x plus 2. And so if I were to run that function on 5, you'd multiply by 3 by 5, and you'd add 2, and you'd get 17. And actually, before we go any further, let's exercise some kernel hygiene here. And let's quit the kernel, and let's load this up. All right. So we've got it, and we can see that, in fact, it works. But there's a second way of describing what we're doing here, and that's as the composition of two functions. The first function takes a number and it multiplies it by 3, and the second function takes that and takes it as input to a function that then adds 2. So we have two functions here, tripler, which multiplies by 3, and add 2, which adds 2. So we could compose those two functions so that they act together. And the way we would do that is we would take the last operation first with a head of composition. We take the last operation first, and then we put the first operation. So the order of the arguments to composition is the opposite of the order in which we want the functions to be applied. And you can then name that composition, just like you can basically name anything in Wolfram language, and we'll call it compose-L. And you can see that it's actually output this funky thing at star. That is the syntactic sugar for conventional composition. So with this, we can apply composal to an argument, and you'll see that it produces 17. And I'm thinking, really, I'm sort of spoiling the drama here. Let me get rid of all the outputs. Let's go back to where we are. Okay, so composal of 5 is 17. Now, we didn't actually have to name the composed function. We could have just evaluated this code here, where I say add 2, at star tripler, that does the composition, and apply it to 5. And you'll notice it's first applying the tripling, and then it is adding 2. And that's important because if you added 2 to 5, you'd get 7, and if you tripled that, you'd get 21, which was not the intent. So you need to just be aware of order of operations here. All right. Now, having shown you composition, I'm probably not going to use it much again. But I think it's important that you see it. Many people think of composition this way. Instead, I want to show you something called write composition. And in write composition, the arguments to right composition are listed in the order in which the function is performed. So first you do tripler and then you do add 2. And we'll call this right composition composer, and we can apply it to 5 and we get 17. Or we could write it this way. You don't have to name it. Just say tripler /*, / is the syntactic sugar for right composition, / add 2, and apply it to 5. And when you see right composition, I want you to think of it as meaning and then. So triplet, and then add 2. I just told you how to compose operators or functions, but I really didn't emphasize what an operator was. And I don't know if we need a precise definition. An operator is a function that has 1, maybe 2 arguments to it. It would be unusual to see an operator that had 5 arguments to it. And let me just show you some operators. Some are built into the Wolfram language, like sine. So we can say sine, or what is sine of pi. Round is an operator. So we can say what's round of 3.14. And we can create operators that might start out life in some sense as having multiple arguments, but we boil it down so that there's only 1 argument. So for example, you can round to things other than the nearest integer. You can round, for example, here to the nearest 10th. And what we're doing, though, here is we're saying, let's create a function, and the only thing you have to give it is the number that you want rounded to the nearest 10th. So I'm going to take this operator here and apply it to 3.14, and I'm going to get 3.1. Or, and again, let me just get rid of some of these outputs that you're not supposed to see yet. I could create an operator named blendMe, and what blendMe does, let me just move this up here. What blendMe does is it applies blend, and blend can certainly take the following type of structure. Let's look at blend. Yeah, it takes the colors that you want blended together, and then it tells you how much do you want to emphasize in this instance, the second color. But how do we write that? Well, one way we could write that is to say what we want to do is to take a data structure, a list, and apply blend to it. So here's blendMe of the list, and the first part of the list is blue-red, and the second part is 0.1, meaning we don't want to place too much emphasis on redness. We want it to be mostly blue. And so if I say, what is blendMe of this list, it's going to say, okay, the first argument is blue-red, and the second argument is 0.1. And we get something that looks like mostly blue with a little bit of reddishness in it. All right, here's another operator. It's based on map. And we can, instead of what we tend to do, or what I've tended to do, is to say map f over 1 to... And that's totally fine, but we've got 2 arguments to map here. What we're going to do here is to create an operator map of f. And what map of f says is, whatever you see following map of f, map f over each of those elements as to what you see. So here I'm taking map f of 1, 2, 3, 4. Okay? And again, I could name map of f. I could call it mapf. And I could say, what is mapf? Mapf is map of f. And then I could say, what is mapf of 1, 2, 3, 4? And it would work splendidly. Okay? So that's the using map, an operator form of map. Or supposing you want to write an operator form that works on a lower level of the expression. You could create this operator here, which basically says when you see the next argument, map f over it, but at level 2. That is not f of 1, 2, 3, f of 4, 5, 6, but f of 1, f of 2, f of 3, f of 4, f of 5, f of 6. So I could name this map at 2, and then I could say what is map at 2 of this little matrix here. And it does what I said, f of 1, f of 2, f of 3, f of 4, f of 5, f of 6. All right, let's go back to the original code. And you can do the same thing with basically whatever function you want. Like, here's an operator. The plot function can take lots of arguments. It can take what are you trying to plot, what domain are you trying to plot it over, various options. And I'm going to reduce this down to a single thing in which the only argument is what are you trying to multiply by x when you want to plot the sign of that expression. So we'll call that plot op. And now if I say plot up of 3, it's going to plot a sine function with a high frequency of 3. And I could say what's plot up of 9, and it would come up with an even higher frequency. Or I could say plot up of 0.3, and it would come up with a very low frequency plot. So the idea here is in some sense to simplify the plot function so that it only takes a single argument. And so one could imagine then, and maybe I'm hinting at pipelines, that supposing the pipeline had thus far produced a 3, you could then use the plot op operator to take just that 3 and turn it into a nice picture like this. You should also know that there are resource functions that create operators. I'm going to use map level a fair amount. Every once in a while I'll use apply level, and a few others, but you'll see map level a fair amount. The idea here is that map level of f at level 2 is basically, let's just see what it does. Right, it does exactly the same thing as map of f of oomph applied at level 2, not oomph, I really should say pound, and then I'll just copy this material down. And it's the same code, but instead of having this arguably ugly pound sign and an ampersand that's a little confusing, this is just telling you, look, take map f at level 2 of whatever you see next. Okay? You should know that if you want to take a function and turn it into an operator, the function you're going to often want to use to do that is called curry applied. I'm not going to spend time on it now. I'm just going to let you know if you ever want to do this. This is where you would look up curry applied in the Wolfram Language documentation. So now that we know how to make operators, we can just pipeline them, compose them as I did before. Here I'm going to take an abstract operator f and then g, and we'll apply that to 1, 2, 3, 4. And you'll see, first we f 1, 2, 3, 4, and then we g the result. Or here's an example where the first thing I do is to map f over the 1, 2, 3, 4, and then I g the result. So you've got g of f of 1, f of 2, f of 3, f of 4. All right, now, many people write Wolfram Language code from the inside out. You sort of start with f of x and you say, let's g that. And that's fine. There is another way to do it, which looks a little more like traditional old school procedural programming. And here's how you do it. You say, let's start with x. And here's what we're going to do after we see x. First, we're going to f it, and then we're going to take whatever comes out of the f and g it. So it's sort of like building blocks or Legos or Scratch, if anyone's seen the computer language Scratch. Here's another example that I think might be helpful. Here I've got these complicated expressions. I want to make a parametric plot of them in 3D with various options, and then I want to frame it with the frame being lighter yellow, and then I want to rasterize that, meaning make sort of a pixelated picture of it with a certain resolution. But that's awfully difficult to read, I think, and maybe what I want to emphasize is what's going on with these expressions. So here's how we could rewrite this. Here's the output, by the way. Here's how we could rewrite this in an operator pipeline postfix kind of way. Start with the expressions, and then here's what we're going to do. First, we're going to make a parametric plot of it. You'll notice the little slot there to turn this sort of into an operator, and then let's take the output from that and frame it, and then let's take the output from that and rasterize it. And indeed, I could, and if I do this, it should give me the same thing. And indeed, I could basically iconize away some of the complexities so that you could focus on, okay, here's our expressions, we'll make a parametric plot of it, and there's some options to the parametric plot, and then he's going to do a bunch of stuff. So I think often this is a nice way to present code. Okay, let's talk query. So, as I mentioned, query is a functional programming construct that takes a sequence of arguments and creates operator pipelines using right composition. There are a few more things that it can do, but this is what we need to know for this moment. So, here's how you make a query. Let's take a query. It's going to have one argument u, and we'll call our query script capital Q. And to find out what this does, just take normal of it. And if you take normal of a query, it will tell you the pipeline that it's created. Now here, this is not much of a pipeline because there's only one function, and you would almost never use query to build something this simple. But now let's build something a little more complicated that's a little more real. We'll build a two-argument query. First, the argument is u, second argument is v, and to see what it does, let's normal it. And what you can see is that it's a right composition in which first comes v, but it's a map of v, and then we u it. Okay? So here's one where maybe you can see a little better what's going on. It's a two-argument query again. The first argument is to total, and the second argument is to take the second part of an expression. To see what this query, which I'll call Q2, does, we'll normal it. And you can see that what it does is it first takes the second part of every expression in a data structure, such as a list, and then having taken those second parts, it adds them up. So let's see if you can predict what's going to happen here as I Q2 this matrix. Well, let's see. The first thing it does is to take the second part of each part. So that's 2 and 6, and then it adds it up, and so it gets 8. So I predict we're going to get 8. And lo and behold, we do. Okay. We can actually have compositions themselves be the arguments to query. And so here, what I'm saying is, let's normal this, as I've said, and I'll say it many, many times. The best way to figure out what a query is doing is just normal it. And so let's see. For each element in the data structure, it's first going to reverse the order, then it's going to take the second part of the reversed order, and then it's going to add it up. So let's see if we can do this in our head. And when we Q3 this, let's see. First it's going to reverse it, so it's 4, 3, 2, 1. And it's going to reverse this, so it's 8, 7, 6, 5. And the second part of the reversed version of this is 3. And the second part of the reversed version of this is 7. And so we're going to add 3 and 7, and we're going to get 10. Hooray. Okay, so query basically is going to produce this right pipeline of operators, and the question that is probably the hardest thing with query is in what order and at what level are the operators produced. So one way to learn this is just to practice. Make queries and see what it does. So here again, I'm going to query U is the first argument, V is the second argument. Let's take the normal form of that. And you'll see that what it's going to do is it's going to map V, and then it's going to take U of that. So one thing to realize is that query, it doesn't need any data. There's absolutely no data here. There's just functions. And just as you can have a function in Wolfram language, like take something and square it, or take the sign of something, without having any argument to which to apply it, so too with query. Second thing I want you to notice is that it's always producing right compositions. And the third thing to notice is, again, to repeat, normal is going to help you figure out the order of operations. So let's look at this query. This is a 3-argument query. Group by F is the first argument, G is the second argument, H is the third argument. Let's see the order of operations. Okay, so the first thing it's going to do is group the data by F, according to its Fness, and then we're going to map something over the output of group by F. That is, group by F may produce a list of items, or possibly an association of items, and then we're going to map over the values of that association. How are we going to do that? Well, first element of map is we're going to submap H over the values of the association, and then we'll G the result. I will cheerfully concede this is a little hard to understand because of the nested maps. And so I think it would be very nice to rewrite this in the following way, making use of the map level operator that I mentioned earlier in the video. First, we're going to group by F, then we're going to map H at level 2 over the outcome of F, and then third, we're going to map G over the outcome from having mapped at level 2. So maybe I could be concrete here. Let's, instead of mapping by an abstract function f, let's map by whether the number is even. And let's just take this pipeline and we will apply it to the list 2, 3, 4, 7, 9, 11, 12, oops, I forgot 11, 12, 0. Okay, so let's see. First it's going to split it into 2 lists in which we'll have the 2, 4, 12, 0 list and the 3, 7, 9, 11 list. Then it's going to map H over that, and then it'll map G. So here we go. All right. So for those that are even, you can see it's putting H in front of all of the even numbers and then G-ing that. And then here it's putting H over all the odd numbers and it's G-ing that result. So hopefully that clarifies things. I told you that query produces a right composition of operators, and it obviously has to do something to figure out what order to put those operators in. I now want to tell you some of the principles that query uses. The first principle is LIFO, last in, first out. This is the default theory. We'll see it's not always the rule, but by default, LIFO. So that in the query above here, where you have U followed by V, V is last, and therefore it's first in the pipeline. Ignore for the moment why I'm mapping it. Just realize that the V is coming before the U. Okay? And so that's one principle. Wolfram language is maybe just like law. There are always exceptions, and an exception to the LIFO principle is where it really doesn't make sense to order the operations in a LIFO way. Suppose, for example, we had some huge passenger database and we want to get the age of the first 3 passengers. You know, we could go through the entire data structure and extract out the ages of everybody and then just get the first 3 passengers' ages. But that would require a pass through all the data. Instead, it would be a lot more efficient if you just took the first 3 passengers and went through however many fields you have on them, 40, 50, or whatever, and pick out the age. So that's at least the concept that Mathematica wants to implement. But you can't just implement a concept, you have to have something concrete. And so the way that Wolfram does it is to look at the operators and based on their form decide that certain of them should cut ahead in line. And the idea is that Wolfram sort of descends through the expression tree, and ordinarily it doesn't do anything until it comes back up. But for some operators, it's going to do it on the way down. Those are called descending operators. When in doubt, assume that an operator is ascending, and what it means, if it's ascending, that means it's going to be in the ordinary order. All right, I know that's hard to understand in the abstract, so let's talk about a descending operator, and maybe one of the most obvious is select. So let's look at a query here. And you can see there are 2 arguments. The first is a select, and the second is a map at. And so what the select does is it picks those values for which the total is even, those lists for which the total is even, and this thing just adds 1 to every element in the second position. So supposing the select is executed first, well, let's look at each of these. There's 3 and 4 and 5 and 7. The total of 3 and 4 is 7, which is odd, so that wouldn't be picked. The total of 5 and 7 is even, so that would be picked. And then we would add 1 to the second element of that, and so we would get out 5 and 8. So that's one candidate. If we don't do it in LIFO order, we do it in not LIFO order. But what if we do it in LIFO order? Well, we add 1 to each one at the second level, and so that would get us 3, 5, and 5, 8. And now, which of those totals are even? It would be the one that's 3, 5. And so that's our other candidate solution. So let's see which one wins. Let's run it. And 5, 8 wins. So it's doing it with the select executed first. And you can see how order of operations makes a difference. Okay, so there are a number of Wolfram language functions that are like select in that they go ahead. And all of them ultimately become something called general utilities slice. I don't think you need to know about that, but if you see functions like span, which kind of takes a range, or take, or key, or the resource function slice, those get put in ahead of time. So that if we look at, here are some queries, that's going to get converted to a slice because it's a span, that's going to get converted to a slice, and this is going to get converted to a slice. Okay? And so slices come ahead of time. What else should you know about slices? When you see a string as an argument to a query, the kernel thinks what you mean is query key A, and then it's going to say that's a slice and it's going to come in ahead of time. So, see, slice, slice. So let's look at what this query is going to do. This is a slice, and so it's going to come in ahead of time. So it's going to say, oh, I'm going to grab the A part of this, and I'm going to have just the association A goes to 3, and I'm not going to have anything with B goes to 4. And then I'm going to F that. So let's see what happens when we do that, and we get F of 3. Again, the A slice grabs the value associated with A, that's 3, and then it Fs. Okay? And if you had any question about what the order of operations was, I hope by this time you know that what you do is normal it. First A it, then F it. All right, there are variants of select, select first, key select, that are also descending. What else is descending? Deletes. If you have data that you want to get rid of, you might as well get rid of it first. And so various functions that delete tend to be descending operators. Here I'm going to delete duplicates. Here I'm going to delete missings, and you can see that even though the G ordinarily would come first because it's last and we use LIFO, because delete duplicates is a descending operator, it gets ahead in the chain. Same thing for delete missing. Wolfram language is maybe just like law. There are always exceptions, and an exception to the LIFO principle is where it really doesn't make sense to order the operations in a LIFO way. Suppose, for example, we had some huge passenger database and we want to get the age of the first 3 passengers. You know, we could go through the entire data structure and extract out the ages of everybody and then just get the first 3 passengers' ages. But that would require a pass through all the data. Instead, it would be a lot more efficient if you just took the first 3 passengers and went through however many fields you have on them, 40, 50, or whatever, and pick out the age. So that's at least the concept that Mathematica wants to implement. But you can't just implement a concept, you have to have something concrete. And so the way that Wolfram does it is to look at the operators and based on their form decide that certain of them should cut ahead in line. And the idea is that Wolfram sort of descends through the expression tree, and ordinarily it doesn't do anything until it comes back up. But for some operators, it's going to do it on the way down. Those are called descending operators. When in doubt, assume that an operator is ascending, and what it means, if it's ascending, that means it's going to be in the ordinary order. All right, I know that's hard to understand in the abstract, so let's talk about a descending operator, and maybe one of the most obvious is select. So let's look at a query here, and you can see there are 2 arguments. The first is a select, and the second is a map-at. And so what the select does is it picks those values for which the total is even, those lists for which the total is even, and this thing just adds 1 to every element in the second position. So supposing the select is executed first, well, let's look at each of these. There's 3 and 4 and 5 and 7. The total of 3 and 4 is 7, which is odd, so that wouldn't be picked. The total of 5 and 7 is even, so that would be picked. And then we would add 1 to the second element of that, and so we would get out 5 and 8. So that's one candidate. If we don't do it in LIFO order, we do it in not LIFO order. But what if we do it in LIFO order? Well, we add 1 to each one at the second level, and so that would get us 3, 5, and 5, 8. And now, which of those totals are even? It would be the one that's 3, 5. And so that's our other candidate solution. So let's see which one wins. Let's run it. And 5, 8 wins. So it's doing it with the select executed first. And you can see how order of operations makes a difference. Okay, so there are a number of Wolfram language functions that are like select in that they go ahead. And all of them ultimately become something called general utilities slice. I don't think you need to know about that, but if you see functions like span, which kind of takes a range, or take, or key, or the resource function slice, those get put in ahead of time. So that if we look at, here are some queries, that's going to get converted to a slice because it's a span, that's going to get converted to a slice, and this is going to get converted to a slice. Okay? And so slices come ahead of time. What else should you know about slices? When you see a string as an argument to a query, the kernel thinks what you mean is query key A, and then it's going to say that's a slice, and it's going to come in ahead of time. So, see, slice, slice. So let's look at what this query is going to do. This is a slice, and so it's going to come in ahead of time. So it's going to say, oh, I'm going to grab the A part of this, and I'm going to have just the association A goes to 3, and I'm not going to have anything with B goes to 4. And then I'm going to F that. So let's see what happens when we do that, and we get F of 3. Again, the A slice grabs the value associated with A, that's 3, and then it Fs, okay? And if you had any question about what the order of operations was, I hope by this time you know that what you do is normal it. First A it, then F it. All right, there are variants of select first, key select, that are also descending. What else is descending? Deletes. If you have data that you want to get rid of, you might as well get rid of it first. And so various functions that delete tend to be descending operators. Here I'm going to delete duplicates. Here I'm going to delete missings, and you can see that even though the G ordinarily would come first because it's last and we use LIFO, because delete duplicates is a descending operator, it gets ahead in the chain. Same thing for delete missing. Okay? Well, Wolfram language is maybe just like law. There are always exceptions, and an exception to the LIFO principle is where it really doesn't make sense to order the operations in a LIFO way. Suppose, for example, we had some huge passenger database, and we want to get the age of the first 3 passengers. You know, we could go through the entire data structure and extract out the ages of everybody, and then just get the first 3 passengers' ages. But that would require a pass through all the data. Instead, it would be a lot more efficient if you just took the first 3 passengers and went through however many fields you have on them, 40, 50, or whatever, and pick out the age. So that's at least the concept that Mathematica wants to implement. But you can't just implement a concept, you have to have something concrete. And so the way that Wolfram does it is to look at the operators and, based on their form, decide that certain of them should cut ahead in line. And the idea is that Wolfram sort of descends through the expression tree, and ordinarily it doesn't do anything until it comes back up. But for some operators, it's going to do it on the way down. Those are called descending operators. When in doubt, assume that an operator is ascending, and what it means, if it's ascending, that means it's going to be in the ordinary order. All right, I know that's hard to understand in the abstract, so let's talk about a descending operator, and maybe one of the most obvious is select. So let's look at a query here. And you can see there are 2 arguments. The first is a select, and the second is a map-at. And so what the select does is it picks those values for which the total is even. those lists for which the total is even, and this thing just adds 1 to every element in the second position. So supposing the select is executed first, well, let's look at each of these. There's 3 and 4 and 5 and 7. The total of 3 and 4 is 7, which is odd, so that wouldn't be picked. The total of 5 and 7 is even, so that would be picked. And then we would add 1 to the second element of that, and so we would get out 5 and 8. So that's one candidate. If we don't do it in LIFO order, we do it in not LIFO order. But what if we do it in LIFO order? Well, we add 1 to each one at the second level, and so that would get us 3, 5, and 5, 8. And now, which of those totals are even? It would be the one that's 3, 5. And so that's our other candidate solution. So let's see which one wins. Let's run it. And 5, 8 wins. So it's doing it with the select executed first. And you can see how order of operations makes a difference. Okay, so there are a number of Wolfram language functions that are like select in that they go ahead. And all of them ultimately become something called general utilities slice. I don't think you need to know about that, but if you see functions like span, which kind of takes a range, or take, or key, or the resource function slice, those get put in ahead of time. So that if we look at, here are some queries, that's going to get converted to a slice because it's a span, that's going to get converted to a slice, and this is going to get converted to a slice. Okay? And so slices come ahead of time. What else should you know about slices? When you see a string as an argument to a query, the kernel thinks what you mean is query key A, and then it's going to say that's a slice, and it's going to come in ahead of time. So, see, slice, slice. So let's look at what this query is going to do. This is a slice, and so it's going to come in ahead of time. So it's going to say, oh, I'm going to grab the A part of this, and I'm going to have just the association A goes to 3, and I'm not going to have anything with B goes to 4. And then I'm going to F that. So let's see what happens when we do that, and we get F of 3. Again, the A slice grabs the value associated with A, that's 3, and then it Fs. Okay? And if you had any question about what the order of operations was, I hope by this time you know that what you do is normal it. First A it, then F it. All right. There are variants of select first, key select, that are also descending. What else is descending? Deletes. If you have data that you want to get rid of, you might as well get rid of it first. And so various functions that delete tend to be descending operators. Here I'm going to delete duplicates. Here I'm going to delete missings, and you can see that even though the G ordinarily would come first because it's last and we use LIFO, because delete duplicates is a descending operator, it gets ahead in the chain. Same thing for delete missing. Okay? Well, more descending operators. The various sorts are descending. So if we have a query and the first argument is sort and the second argument is some function G, LIFO doesn't apply. It's not G / sort, it's sort / G. Sort by, same thing. Reverse sort, same thing. So let's look at all of these, and you can see in all of these the sorting operation comes first. A footnote. Form matters. Wolfram language is not smart enough yet to realize that this hand-constructed operator, where I've used the ampersand and the pound sign to make an operator, is the same thing as this sort by. And same issue here and here. And so when I normal these, you're going to see that it's going to be G slash dot slash star sort by pound F ampersand. Okay? Or map G, map G, map G. So form matters. And again, if you're confused, you're not sure, just normal it. Okay. Values. Values is a function that just gets the values from associations, and it's a form of slice, and so it goes ahead. All right, enough on taking things out of order for now. Let's turn to a different subject, which isn't really about a query. It's more about how it arises all the time with query, but it's how various Wolfram language functions deal with association. So let's look at a list line plot here. Here's our XY data, and there's our list line plot. But what if instead of just having a list of points, we had an association of points? A is 1, 3, and B is 2, 8, and C is 4, 9, etc. Let's see how list line plot handles the association. And what you can see is it's the same line, but now it's labeling the points. And so it's sort of as if list line plot is seeing through the association, although it's smart enough to pick up that the keys might be useful labeling information. All right, let's see how we can make use of this with some real data, and I'm going to try and make some labeled bar charts. Okay, so the goal is to get code that groups the passengers on the Titanic by their cabin class and their sex, and then to see what fraction of each such grouping survived. So Wolfram Language comes with a Titanic database, and there it is. So here's our Titanic data set. You can see we've got information on the cabin class, the age, the sex or gender, and whether they survived or not. And we've got information on 1,309 passengers. Some of the information is missing, which is what those dashes represent. All right, so let's form a query that's going to make this bar chart. And let's start simple, okay? So what we want to do is first we'll group by class, and then within each class we'll group by sex. And then for all of the sex groupings, we will get information on survival of each person. Okay? And so that's our simple query. If you're curious about the order of operations, first we group by class, then for each class we group by sex, and then for each class and sex we get whether the passenger survived or not. All right, if we run this against the Titanic, you can see that we've got here sort of the top level groupings. Here's the second level grouping. Notice it's not sorted. There's an inconsistency in the order. That's fine. And here are the people, the survival data on each of them. So if I click on this, I should see 144 true-false values representing the survival of the females in first class. And indeed, that's what I see. Okay, so just so you're clear on that, I guess I programmed this in. Let's get the first class males and see what they look like. And again, it's the same idea, true, false, blah, 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 blah. All right, so what we want is the fraction of each of these lists that's true. We want to know the fraction that survived. So I'm going to write a little function that makes use of the proportions resource function, so that if I were to say proportions of 3, 4, 3, 4, 3, 5, 2, 3, 4, 4, 4, it's going to tell me that 1/12 of those numbers are 5, and 1/12 of those numbers are 2, and 1/2 are 4, and 1/3 are 3. So that's what the proportions resource function does. And then I want to know what fraction are true. So one way I could do this would be to just say, of those, get me the true ones. That's what that little function does, and you can see the right composition here. Okay, so just so you're clear on that, supposing we take this first class male survival here, I'm going to normal it for reasons that don't need to concern us, and I'm going to take the fraction that survived. And the reason that it failed is I forgot to evaluate this line of code. Now it's evaluated, and now it's going to work flawlessly. And it turns out that of males in first class, 61 179ths survive. But I don't want it just for first class males. I want it for all of the cabin class and sex groupings. So we're going to revise our query. We're almost there. And first we group by class, and then we group by sex, and then we get the survival information, and for each of those pieces of survival information, we get the fraction that survived. So again, normal, almost there, and you can see first we group by class, then we group each subgrouping by sex, then for all of them we figure out who survived, and we compute the proportion that's true. All right, if I run that on the Titanic, I get just the data I want. I can see what the survival numbers are, but I didn't just want a chart. I want a bar chart. I mean, I don't want just numbers. I want a bar chart. And so all I have to do is come back to this first level and say, take the output and make a bar chart out of it. And then I've got just some labels on it. So let's look at this query. Again, here it is in normal form. First you group by class, then you group by sex, then you get the survival information out of each subgrouping. Then for each subgrouping, you determine the proportion that's true, and then you take all of it and you stick it into a bar chart. Or, if I wanted to write it a little better, I think, I would use map level rather than these nested maps. Here's what we'd get. But in any event, let's run our query on the Titanic data, and look at this. We get an interesting bar chart. And actually, to me, what's interesting is gender really mattered in determining whether you got on that lifeboat or not. Even males in first class did worse than females in third class. And for males, once you were out of first class, things weren't looking very good. And we ought to check just to make sure my handcrafted query in which I use the map level resource function works. And okay, once again, professor, remember to evaluate your code. And oh, by the way, do you see how we've got some currying going on there? I think I mentioned that earlier in the video. And yes, our handcrafted query worked. Okay, let's put our investment in learning about query to some use, and I've got a question. Clearly, from what we've seen, being a woman helped in terms of surviving on the Titanic, but among women, did age matter? So let's do the following. My idea is I'm going to break the women up into decades of age, and then I'll see how they did on the Titanic. So how are we going to do that? Well, first of all, we're only going to look at women, and we're only going to look at women for whom we have data on age. Then what we're going to do is we're going to compose that grouping by the decade of age. Don't worry about quotient. It's sort of like division without remainders. And to make things nice at the end, I'll sort the results. And from here on in, we've seen this before. For each grouping that I create for each decade of age, get the fraction that survived, turn it into a number, and it'll do this survive thing first. So let's run that on the Titanic. And there we go. And so you can see that within women, age mattered, and old people did real well. Children actually didn't do so well. The women and children first. I think they forgot the children part. In any event, that's what we get using our query. All right, what about this? Let's try this. What I want to do is I want to get the data in the form in which, if we were doing statistics, we'd call them the independent variables. If we're doing machine learning, we might call them features. If we were doing causal analysis, we might call them covariates. Whatever, we want the stuff we're using to predict on the left-hand side of a rule, so class, sex, and age, and we want whether they survived or not to be on the right-hand side of the rule. So this is actually pretty easy. We just say for every passenger, form this rule. And then at the end, I want to take it out of a data set, and because there are 1,300 entries, I don't want all 1,300 entries. We'll just get a couple of lines. All right, so that's how we can put it in this form, and later in the course we'll learn that once we have it in this form, we can run machine learning. We can say classify people based on whether they survived, and it'll do something, a random forest or a decision tree or something to figure out whether people on the Titanic survived. Okay, let's try another question. Supposing we want to classify, and we want to do it in a way that reduces the entropy of the survival distribution more. You're going to need to hearken back to the discussion elsewhere in this course on the entropy of distributions, but we want to reduce the disorder, and as I mentioned during that talk, that's often useful. That's part of machine learning algorithms that are based on decision trees, such as decision trees, or decision trees on steroids like random forests. So this is not hard. What we're going to do is we're going to get the survival information on everybody. That's going to form a list, and Wolfram Language has an entropy function built in. So if we just look at this query just again, so we are clear on the order of operations, this is a LIFO query, no exception applies. So we're going to map survival over all the data and then take the entropy of the resulting list and then get the numeric value of that. So when we do it based on survival, we get our entropy down to 0.665. I guess it would be a nice thing. Let's get the entropy of everybody. Right, I'm sorry, I just did. I just got the entropy of everybody. I didn't group anything yet. Sorry. Now, let's group people by cabin class and figure out the weighted entropy. So the way we're going to do that is I'm going to make a function that takes a list and for that list computes its entropy and the length of the list. I'll use through to do that. So we're going to get two numbers. Maybe the entropy is 0.59 and there are 26 people in the list. So we're going to get those for each of the groupings. What we then need to do is to turn this into weighted data from which we can take the mean. You may recall this from our discussion of entropy reduction. And so let's suppose our data looked like this. What could we do? Well, we could take this matrix and transpose it. I'm not sure if we've seen transpose already, but the idea is to make the columns become rows and the rows become columns. So now instead of having a matrix that is 3 rows by 2 columns, we have a matrix that is 2 rows by 3 columns. And what we can then do, this is exactly the form that weighted data wants. If we look at weighted data, you can see first it wants the numbers and then it wants the weights associated with them. And that's exactly what we have. And so we then just need to apply weighted data to that transposed data. I'm using the double @ sign here as a shortcut for apply. I could write it this way. Probably I should have written it this way since that's what I've done elsewhere in the course, but I succumbed to the desire for syntactic sugar. In any event, and why isn't it doing it? It's not doing it because I forgot to evaluate. All right, now I've evaluated it. We get weighted data. If I do it this way, we get the same thing. Okay, so now let's put it all together. let's group by class. We don't care at this point what the names of the classes are. We just want the values in them. And so let's get the values. Let's transpose those values. Apply the weighted data. Take the mean of the weighted data, get the numeric value. And let's actually look at the order of operations here. Okay, so you can see what is actually going on here. I'm not sure how instructive that is. And if we run it, we reduce the entropy down from its original value of 0.665, and by classifying by sex, we get it, classifying by cabin class, we get it down to 0.61. If we want to do it by sex, it's exactly the same code. The only little change is what we're using to group by, and we're grouping by sex. And when we do it that way, we get our entropy down to 0.522, and so we can see that grouping by sex, it reduces the disorder in the survival data more than grouping by cabin class. Okay, let's take a pause here. Okay, into the home stretch. I talk in the written version about 4 complications. I think some of these you can read on your own, such as what happens when you have both ascending and descending operators that are composed and that are part of an argument to query. I think you read that on your own and learn about it. Second complication is group by, but actually in our examples we kind of saw how group by works. It tends to come first. And so it's a descending operator that we've talked about. So I think I can spare you a description. I think I am going to spare you subqueries. This one, complication 4, I feel we need to talk about. Okay, it's what happens when you don't want to do anything at a particular level. You sort of need a placeholder to tell it don't do anything at a particular level. So let's look at this data. It's my data, and if I look at the dimensions of my data, it's a 3 by 4 by 5 table, 3 rows by 4 columns by 5, whatever you call the ranks. Okay, so what I want is the last part of the third part of each of the 4 by 5 tables. So let's eyeball this. Here's a 4 by 5 table. I want to take, here's the third part, and that little 32 is the last part of the third part. And I want the last part of the third part of the second 4 by 5 table, and the last part of the third part of the last of the 4 by 5 tables. So I want some code that's going to get my 32, 20, 50 in a list. So could I do this? Could I say get me the last? And no, that gets me the last entire piece. Now I could do something like this, where I say for each 4 by 5 table, get me the third row and then get me the last piece. That would actually work, but to me that's kind of ugly, and let me show you the alternative. Okay, let's look at the normal form. This is actually in some ways harder than it might appear. What's that all doing? That all is saying do nothing at the top level. Just leave it alone. And what we have here is at the second level, this is why I wish they would use map level. At the second level, get the last element. And so if we look at our original data here, it's getting the 90 and the 15 and the 32 and the other 32 and the 24 and the 20 and the 20. And then what it's doing is it's saying, okay, and of those, get me the third one. Okay, and so when you do that, it's no longer getting the 90, the 15, the 32, and the 32. It's only picking the third of those, the 32, and it's not getting the 24, the 20, the 20, and the 50. It's getting the third of those, which is 20, and it's not getting the 33 and the 89, the 50, and the 74 anymore. It's getting the 50, which is the third of them. And so if you want to do nothing at the top level or at any given level, just put in all right? And if we run the query, we can see that it actually succeeds. Okay, I think you're going to live your life for right now without knowing about syntactic sugar for MAPAT. And so this concludes our discussion of operator pipelines and query. I know this material is difficult, but frankly, all database languages are kind of difficult in figuring out how to best analyze the data, but it's a useful exercise. It's a good way of thinking about data. And once you get some practice with Wolfram Language and query, I think you'll see that it can actually do some pretty awesome things. So, thanks for your attention.